Dear students of veterinary, last class we have discussed different theories to understand the structure of atom. Today I am going to discuss dual behavior of matter, or specifically dual behavior of an atom. So first let me say matter. What is a matter? Any object having characteristic mass, energy, and occupies characteristic space in the universe is called matter. And matter we can classify by two ways. One that is, before going for the classifications, let me give some introduction again. So let me say what is universe. Universe, I can now say, is nothing but a system and surroundings are called universe. And in the system and surroundings, we are now seeing matter and energy, it is present. So, let me come back now. So, matter, I want to classify by two ways. One is physical classification based on physical properties. Chemical classification based on chemical property. This is the fundamental chapter. The first chapter itself we have discussed. So based on physical properties, we can classify into 5 types. Matter can be classified into 5 types. One, solids, liquids, gases, plasma, Bose-Einstein condensate. Solid, liquid and gases are well known to you. I need not explain. What is plasma? Plasma is nothing but heated gases to produce ions and electrons. What is Bose-Einstein condensate? That is, gas at a very low density, cooled at 0 degree temperature, is behave as a matter. It is called Bose-Einstein condensate. The same way, I can classify matter by two ways. One is based on physical changes. I will classify as substances and mixture. Substances I can classify into 2 types, elements and compound, based on chemical changes. And elements further I can classify into 2 types, atom and molecules. So kindly, if you want more detail, kindly refer the basic concept of chemistry, first unit. Okay, let's come for dual behavior of matter. When we say dual behavior of matter, we are going to give concentration only for atom because we are studying atomic structure. So, matter behaves as a wave as well as a particle. Matter may be a macro or micro. Here, we are confined only micro matter. Kindly follow. Like atom, molecule, electron, proton, neutron, etc. So here we are now discussing only under the atomic structure. So we are going to discuss regarding dual behavior of atom. That is, atom behaves as a wave as well as a particle. Another interesting information I want to give here. All electromagnetic radiation available in the atmosphere behave like as wave as particle. So, matter, as I already pointed out, we can behave as a wave, behave as a particle. Okay, let me come for electromagnetic radiation. What is electromagnetic radiation? Electromagnetic radiation is a form of energy emitted and absorbed by the charged particles, which exhibits wave-like behavior as well as particle behavior as it travels through the space. Very, very interesting information. So, in order to understand, different theories are proposed to understand the electromagnetic radiations. So, what are the important electromagnetic radiation? Let me come later. So, as I already pointed out, there were 2 theories. Different theories were proposed to understand electromagnetic radiation. Mainly, one, Maxwell classical theory or wave theory, quantum theory or particle theory. So now let us confine to atom only. Okay. First let me take Maxwell classical theory or wave theory. According to Maxwell classical theory, electromagnetic radiation is considered as a wave and constituted of electric and magnetic fields which are mutually perpendicular to each other and also perpendicular to the line of propagation. So suppose the electromagnetic radiation is the atom. So atom is considered as a wave constituted of electric and magnetic field which are mutually perpendicular to each other and to the direction of propagation. So just see, this is the diagram for this one. So what this is now can say electromagnetic radiation, and this is the magnetic radiation. Kindly follow. That is the two radiations. So they are mutually perpendicular to each other and also perpendicular to the line of propagation. Kindly follow. Now, what are the characteristics of a wave? So, if you consider atom is a wave, what are the characteristics of wave? Wavelength, number one, lambda represented by frequency represented by nu, wave number nu bar, velocity c, amplitude height. These are the characteristics of any electromagnetic radiation, specifically in this case atom. So let me discuss one by one to understand the idea. What is wavelength? The distance between two nearest peaks or crest or trough is known as wavelength. It is expressed in meter. Just see, this is the wavelength. The distance between two peaks. Peaks or crest or trough. And below, that is, we can see here, this is nothing but trough. The top one peak or crest, the below one trough. This distance we will call it as lambda, wavelength. Okay. Come for frequency, another characteristic property of an atom, that is a matter. The number of waves passes through a given point in 1 second is known as frequency of the wave. It is expressed in hertz or CPS, cycle per second. Nu equal to C by lambda. Okay, let me come back. Next one. Velocity, C. The distance travelled by a wave in 1 second is known as velocity of the wave. It is usually represented by C expressed in meter per second, that is given by C equal to nu into lambda. Next one. Wave number, that is nu bar, nothing but 1 by lambda. What is wave number? Wave number is the reciprocal of wavelength, that is number of wavelength per meter. So I can give mathematically wave number is equal to 1 by lambda per meter. Another characteristic. Amplitude, that is height of the wave, that gives the intensity of the wave. It is the height of the crest or peak or depth of the trough of a wave. It determines the intensity of the beam of light. The light intensity can be determined by the amplitude, height of the peak. Okay. So let me come for some important types of electromagnetic radiation. So I have discussed various characteristics of electromagnetic radiations. Now I want to give some important electromagnetic radiation available in space that we are living. So here, let me go with the first one, the types of electromagnetic radiation. Number one, cosmic rays, wavelength 10 to the power of minus 14 meter. So it is given in terms of the increasing lambda value it is given. Cosmic, so it is having the lambda value 10 to the power of minus 14 meter. Number 2, gamma rays 10 to the power of minus 11 meter. X rays 10 to the power of minus 9 meter. UV rays 10 to the power of minus 7 meter. Next one. Visible rays 10 to the power of minus 6 meter, IR 10 to the power of minus 5 meter, for IR 10 to the power of minus 4 meter, microwave 10 to the power of minus 3 meter. Next one, radar 10 to the power of minus 2 meter, television 10 to the power of 0 meter. NMR, nuclear magnetic resonance, 10 to the power of 1 meter, radio 10 to the power of 2 meter, AC, alternate current, 10 to the power of 6 meter. So these are some examples of electromagnetic radiations. Kindly follow. So here it is given in the form of increasing lambda. Okay, so let me go further. Now I have to give evidences to prove that the atom is behaving as a wave or matter behaving as a wave. That is the most important thing. When you say atom you can say, or electron you can say, anything you can use. So first let me take the experiment, Davison and Germer's experiment. In 1927, Davison and Germer observed that a beam of electrons obtained from a heated tungsten filament is accelerated by using a high positive potential. Kindly follow, this is very interesting. Davison and Germer in 1927 observed a beam of electrons obtained from a heated tungsten. When tungsten was heated, the electrons were emitted and it was passed through a crystal and the electron diffraction observed. Just see here, the nickel crystal was used here, tungsten was heated, the particle emitted is the electrons. So after the diffraction, so it is observed in the photographic plate, we are seeing this is the diffraction pattern for these electrons. And from this diffraction pattern, what is the observation? When this fine beam of oscillated electron is allowed to fall on a large single crystal of nickel, the electrons are scattered from the crystal in different directions, which are allowed to fall on the photographic plate. The diffraction pattern so obtained is similar to that of diffraction pattern obtained by Bragg's experiment on diffraction of X-rays in the crystallography. In crystallographic methods, the determination of interplanar distance D was determined by Bragg by using the L lambda equal to 2d sin theta. So the same pattern is observed here. So it is behaving as a wave. Since X-rays have wave character, therefore electron also have wave character associated with them. Moreover, the wavelength of electron as determined by the diffraction experiment were found to be in good agreement with values of calculated from de Broglie wave equation. De Broglie equation. From the above discussion, it is very clear that an electron behaves as a wave. The first experiment, Davison and Germer experiment, proved that electron behaves as a wave. The second experiment, G.P. Thomson experiment. So what G.P. Thomson did, instead of taking nickel crystal, he took gold foil, and again by tungsten, again beam of electron was accelerated and it was passing through the thin foil and is allowed to fall on the photographic plate. Then this diffraction pattern was observed. What is the explanations? G.P. Thomson in 1928 performed experiments with a thin foil of gold in place of nickel. Kindly follow. In place of nickel, he now used gold. He observed that the beam of electron obtained from tungsten after passing through the thin foil of gold, he received on the photographic plate perpendicular to the direction of beam. A diffraction pattern is observed as before, like X-ray pattern like of Bragg's equation. This again confirms the wave nature of electrons. The third one. So other evidences for wave theories are interference, diffraction we have seen, polarization, These are all you might have studied in physics. These are the evidences to show the electron behave as a wave or atom behave as a wave. Okay, let me go for quantum theory. That is a particle theory. Electron behave as a particle or atom behave as a particle. Number one, based on the concept of black body radiation, Planck in 1901 proved that atoms could not only emit or absorb radiation energy discontinuously in the form of small packets. Kindly follow. Discontinuously in the form of small packets or bundles of energy known as quanta. Kindly follow. Waves are continuous, whereas particles are discontinuous in the form of packets. He proposed an equation for the energy associated with the electron as E equal to hf, where hf is the frequency. He used his original paper. So, in this case, h equal to Planck's constant, where h equals to value 6.626 into 10 to the power of minus 34 meters square kilogram per second. Okay, let me go for the next one. Einstein in 1905 extended this theory and postulated that light energy, like electron, is not only emitted or absorbed in the form of bundles, but also propagated in the form of bundles in space. Each bundle is called as photon, and plural photons. The energy of a photon is given by the expression E equal to h nu, that is nu is the frequency of the photon. Okay, now the main difference is that Planck's equation was used for the energy of electron, while Einstein equation is applied to light. In both cases, the key idea is the energy is quantized. That is the quantum theory. Okay, now what is the proof now? Evidences. J.J. Thomson cathode ray experiment. Experiments show that J.J. Thomson cathode ray experiment for determination of E by M ratio and Mulliken oil drop experiment for determination of charge on electron also shows that electrons behave as particles, or electrons have particle character. Another evidence. When an electron beam from tungsten is allowed to fall on thin sulfide screen through gold foil, a spot of light known as scintillation is produced. A scintillation is localized on the thin sulfide screen. Here, the striking electron which produces it also must be localized, and it is not spread out on that screen. This localized charge character is possessed by only pi particles. So it is the particle character. Very, very interesting information. Another important evidence for particle is photoelectric effect proposed by Einstein. What is photoelectric effect? When the surface of the metal is exposed to light, ejection of electron from the metal takes place. This phenomenon is known as photoelectric effect. Just see here. So we are passing light which is falling on the metal, electrons are ejected. So this is possible only, it's showing the character is particle character. The another important evidence for this particle is Compton effect. What is Compton effect? When a photon hits an electron, its wavelength increases. This phenomenon is called Compton effect. So you take a photon, allow it to hit on an electron, so it will transfer its energy. So there are three possibilities. If hit straightly, if it is going straight, sideways, here or here. So what is observed is, when a photon hits an electron, its wavelength increases. When wavelength increases means energy decreases. So it's the particle character. So we have discussed the matter behaves as a wave as well as a particle, or specifically here, atom behave as a wave as a particle. Next, let me go for dual nature of matter. Dual nature of matter. That is, same atom behave as, it's a proof, it's an equation given by Louis de Broglie wave equation. Dual nature of matter. That is again for applicable both for all electromagnetic radiation or atom or anything. So it's called Louis de Broglie wave equation. According to Louis de Broglie, he proposed that matter is as dual character as a wave as well as a particle. He was awarded Nobel Prize in 1929 in physics for this equation. That is lambda equal to h by mv or h by p. P is the momentum. So let me derive this. Kindly follow. Suppose if your photon is assumed as a wave character like electron, its energy is given by h equal to h nu. This is according to wave theory. H into nu. According to Einstein, if the photon is considered as a particle like electron, its energy is given by E equal to mc square. This is particle theory. So by amalgamation of these two theory, he derived an equation. That means left side energy equal, so h nu equal to mc square. So he derived an equation. Therefore, from 1 and 2 you got h nu equal to mc square. But we know nu equals c by lambda. By substituting, we are getting mc square equal h nu, and we know nu equal to c by lambda. So by substituting mc square sc by lambda, or lambda equal to sc by mc square, or h by mc, or lambda equal to h by m. The h by mv. V is the velocity, m mass. That is equal to hp. P is the mv, momentum. So in the case of light, we will use c. In the case of other matter, we will use v. That is the most important. So this is the famous de Broglie wave equation. Okay. De Broglie pointed out that the above equation is applicable to any matter or particle or electron. The mass of a photon is replaced by mass of electron, and velocity c of the photon is replaced by velocity of electron v. Therefore, for an electron, lambda equal to h by mv, that is equal to h by p, where p is the momentum of electron or particle. This equation is called de Broglie wave equation. Very, very interesting information. Okay, let me come for Heisenberg uncertainty principle. This is most important because even though the two theory proposed, wave theory as well as the particle theory, only quantum theory succeeded, whereas the wave theory fails because of this uncertainty principle. Because the quantum theory accepts this uncertainty principle, take into consideration of uncertainty principle, and successful. Let me come back. Moving objects around us move along in a definite path. The path of an object is determined by its location and velocity at various moments. Thus, a planet moving in the sky has a definite path. Very interesting information. For a subatomic object such as an electron or atom, however, it is not possible to determine simultaneously the position and the velocity at any given instant to an arbitrary degree of precision. Kindly follow. This is the uncertainty principle. What is Heisenberg uncertainty principle? It is not possible to determine simultaneously the position and the velocity at any given instant to an arbitrary degree of precision. This is Heisenberg uncertainty principle, applicable only for micro particle, not macro. Consequently, it is not possible to talk of the path of an electron. The impossibility of the simultaneous determination of the position and the velocity of small particle in motion was first shown by Werner Heisenberg in 1927 to be the direct consequence of dual character of light and matter. Very interesting information. What is the mathematical form of Heisenberg uncertainty principle? This principle is known as Heisenberg uncertainty principle. It is given by delta x into delta p equal or greater than h by 4 pi. So this is the mathematical form of Heisenberg uncertainty principle. The effect of uncertainty principle is important only for the motion of submicroscopic objects. Kindly follow. Only for the motion of submicroscopic objects and is negligible for that of larger objects, macro objects. Quantum mechanical theory, which allows uncertainty principle, I have already informed you. Quantum mechanical theory, that is particle theory, which allows uncertainty principle, was developed during 1920 and it was successful. So it succeeded. Okay, now before concluding, let me point out the differences between wave and a particle. What is the difference between a wave and a particle? Number one, a particle is localized in space. It is a particle localized in space, whereas wave is delocalized in space. Example, when a stone is thrown on water, waves start moving in the form of concentric circles. Okay, second important difference. Particles do not interfere. You take one particle, take another particle. They will not interfere together. The same space cannot occupied by two different particles. Whereas in the case of waves, waves can interfere. That is, two or more waves can occur in the same region of space. Number three, when a number of particles are present in a given region of space, the total value is equal to the sum. Whereas, in the case of wave, when a number of waves are present in a given region of space, due to interference, the result wave can be larger or smaller than the individual waves. That is, interference may be constructive or destructive. So these are the three important differences between particle and a wave. I hope you have enjoyed this concept, that is dual character of matter. That is specifically in this chapter, dual character of atom. Thank you.